Hi, my name is Ali Karudi, and in this video I'll be talking about recursion in C++. In past device solutions to problems, we use the most common technique called iteration. For certain problems, however, using the iterative technique to obtain the solution is quite complicated. This video introduces another problem-solving technique called recursion and provides examples demonstrating how recursion actually works. The process of solving a problem by reducing it to smaller versions of itself is called recursion. Recursion is a very powerful way to solve certain problems for which the solution would otherwise be very complicated. Let us consider a problem that is familiar almost to everyone, and that's the mathematical calculation of factorial. So the factorial of a non-negative integer, which is being presented like this, 0 factorial, or any number factorial, is defined as follows. We know that 0 factorial is always 1, and we know that n factorial is equal to n times n minus 1 factorial. So basically that is the given in mathematics. Remember, these are all about the time that n is a positive integer. The definition of 0 factorial being 1 is important here because later when we discuss the base case, you see how we use this as a base case, right? If n is an integer greater than 0, first we find n minus 1 factorial and then multiply it by n. To find n minus 1 factorial, let's see what we do over there. We actually are going to apply the same thing. So basically, if I want to look at n minus 1, and let me just do it this way. If we're looking for n minus 1 factorial, that is going to be equal to n minus 1, which is the first number that we have, right? Now this time, right, times n minus 2 factorial, right? This is what we actually can see as we go down. You're going to see n minus 2 factorial is going to be n minus 2 times n minus 3 factorial and so forth. As you can see, we are reapplying the same definition again and again and again. So let us look at it in number part. So if you look at 3 factorial, it's equal to 3 times 2 factorial, right? That's how we put it down. And 2 factorial is equal to 2 times 1 factorial. And then we know 1 factorial is equal to 1 times 0 factorial, which in this case, we already know that the equation 0 factorial is going to be resulting to 0. The solution here is very direct after this because now we have 1 times 1 over here, which is going to come up and substitute 1 factorial. Then we have 2 times 1 here, which is going to be the result of 2 factorial, and then 2 is going to substitute here, getting us to number 6, right? So let's talk a little bit about the definitions. The definition of factorial given in this equation is called recursive definition, okay? So pretty much remember the fact that we have 0 factorial equal 1 is being called we have a base case. So this is our base case. And the fact that we know it can be repeated as n factorial equals n times n minus 1 is called a general case, right? So going back to the definition, we say a recursive definition is a definition in which something is defined in terms of a smaller version of itself. From the example we just went through, it is clear that every recursive definition must have one or more base cases. 2, the general case must eventually be reduced to a base case. Look at this general case. When we start running the recursivity, we have to get to the point that we can resolve this to 0 factorial, which is the base case. So at the end of the day, general case must be resolved to a base case. And finally, at the third step, we have to be at the situation that the base case stops the recursion. In our example, as you can see, 0 factorial is equal to 1. We don't have any continuation of factorial over there. So the factorial stops over there. The same way, a function that calls itself is called a recursive function, which is the body of recursive function contains a statement that causes the same function to execute again before completing the current call. Recursive algorithms are implemented using recursive functions. Let us do this with an example. Let me clean this up quickly and give you an example. Here it is. Let's read through it together. So we define the function called factorial, which we pass an integer num into it, right? So the first step is to check if num equals 0. Remember, 0 factorial equals 1, right? So if this is the situation and we are receiving 0, then we return 1 back. So that's the end of it. The function returns 1 and we're all good. Otherwise, which means when num is not equal to 0, we'll return the result of num times factorial of num minus 1. Notice that the function fact is being called from within itself, and that is how recursion actually works. Here you can see how the execution of the statements actually traces. So let's say we call factorial of 3. When we call fact 3, num will be 3, as you just saw it in the function fact, right? Because this is not 0, it returns what? 3 times factorial of 2. But when we call the fact 2, basically we're calling the function again. It's like we're doing this function call. Look at the trace that I have this way, going downward, right? I'm calling factorial of 2, therefore now num is 2, and then num is not 0, so I'm calling fact 2 times number 2 times fact 2 minus 1, which resolves to 1. And as you can see, fact 1 is now called. The same way, next step is to call fact 0. When we come down here, because num is 0, now we return 1, okay? So we return 1 back up there, which is going to be the result in this equation, right? In this case, fact 0 is going to be substituted by 1, so we return 1 times 1, as you can see here. Then we go back up. This time we return 2 times 1 to the top, and then finally 3 times 2, which is getting returned back, and therefore fact 3 returns 6. So the output is going to be at 6. So if we do a cout, we're going to see 6. Let's go back to the code, try this, and then continue. So what I'm going to do here is within main, I'm going to do cout. And the only thing that I'm going to do is call fact and pass number 3 to it. I'm going to add an end line just to make it look good. And let's just quickly run this. And as you can see down here, the result of our calculation is number 6. Okay, so let us note that this example is involving the factorial function, and logically you can think of a recursive function as having an unlimited number of copies of itself. Every call to a recursive function, that is, every recursive call, has its own code and its own copy and set of parameters and local variables. After completing a particular recursive call, control goes back to the calling environment, which is the previous call. The current recursive call must execute completely before control goes back to the previous call. The execution in the example that we had, every previous call begins execution from the point immediately following the recursive call. Okay, now let's talk a little bit about direct and indirect recursion. A function is called directly recursive if it calls itself. A function that calls another function and eventually results in the original function call is said to be indirectly recursive. For example, if function A calls function B and function B calls function A, then function A is indirectly recursive. Indirect recursion can be several layers deep, and this is something that we're going to look at in the future videos. Indirect recursion requires the same careful analysis as direct recursion. The base case must be identified. Remember, guys, if there is no base case, there is no recursion, okay? Also, if there is no general case, there is no recursion. So both of them should be clearly identified, and you should have a stop point. I mean, the base case should be the stop point for the entire um, recursivity. Tracing through indirect recursion can be tedious because you're jumping between two different functions. You must therefore exercise extra care when designing indirect recursive functions. For simplicity, the problems in this video for beginners only looks at direct recursion. So indirect recursivity is being left out for higher level of expertise when people learn more about language and get more familiar with it. Okay, we just want to keep it simple for your understanding. A recursive function in which the last statement executed is a recursive call is called a tail recursive function. The function factorial fact that you're seeing right now is an example of a tail recursive function, because this is here, the last statement is the statement that actually starts the recursivity. For our example, we looked at the sequence of recursive calls eventually reaching a call that made no further recursive calls, and that's the call to 0 factorial. That is, the sequence of recursive calls eventually reached the base case. On the other hand, if every recursive call results in another recursive call, then the recursive function is said to be having infinite recursion. And this is something that we want to avoid. In theory, infinite recursion executes forever, and your computer is going to go to the stall. Every call to a recursive function requires the system to allocate memory to the local variables and formal parameters. The system also saves this information so that after completing a call, control can be transferred back to the right caller. Therefore, because computer memory is finite, if you execute an infinite recursive function in a computer, the function executes until the system runs out of memory and results in an abnormal termination of program. Recursive functions or algorithms must be carefully designed and analyzed. You must make sure that every recursive call eventually reduces to a base call. Okay, now let's look at an example. Okay, this is a Tower of Hanoi example. In the 19th century, a game called the Tower of Hanoi became popular in Europe. This game represents work that is underway in the Temple of Brahma. At the creation of the universe, priests in the Temple of Brahma were supposedly given 3 diamond needles, with one needle containing 64 golden discs. Each golden disc is slightly smaller than the disc below it. The priest's task is to move all 64 discs from the first needle to the third needle. The rules of moving the discs are: first, only one disc can be moved at a time. 2. The removed disc must be placed on one of the needles. 3. A larger disc cannot be placed on top of a smaller disc. The priests were told that once they had moved all of the discs from the first needle to the third one, the universe would come to an end. Our objective here is to write a program that prints the sequence of moves needed to transfer the discs from the first needle to the third needle. As before, we think in terms of recursion. Let us first consider the case in which the first needle contains only one disc. In this case, the disc can be moved directly from needle 1 to needle 3, right? So let us consider this case in which the first needle contains only 2 disks. In this case, first we move the first disk from needle 1 to needle 2, and then we move the second disk from needle 1 to needle 3. And finally, we move the first disk from needle 2 to needle 3. Now let's consider we have a case in which the first needle contains 3 disks, and then generalize this to the case of 64 disks. In fact, to any arbitrary number of disks. Okay? So as you can see, what I'm looking for is a base case and a general case. So let's look at the situation of 3 disks. Okay, suppose that needle 1 contains 3 disks. To move disk number 3 to needle 3, the top 2 disks must first be removed to needle 2. Disk number 3 can then be moved from needle 1 to needle 3. To move the top 2 disks from needle 2 to needle 3, we use the same strategy as before. This time, we use needle 1 as the intermediate needle. As you can see on the screen right now, the solution to the Tower of Hanoi problem with 3 disks is already in front of you. And that is, we move one disk from needle 1 to needle 3, then we move the second one, number 2, to the middle one to get here, right? Then what we do is we move one back on top of 2, and now that this needle is empty, we just need to move 3 over there. As you can see now, 3 is down there. Now next step is to move 1 out, which as you can see is happening here. 1 is being moved out, and now we have 1, 2, 3. 2 is being moved all over to 3, and we get to this point. And then finally 1 is being moved on top of 2, and 1, 2, 3. As you can see from here, we moved all the way to there, okay? So let us now generalize this problem to the case of 64 disks. To begin, the first needle contains 64 disks. Disk number 64 cannot be moved from needle 1 to needle 3 unless all the top 63 disks are on the second needle, right? So first, we move the top 63 disks from needle 1 to needle 2. And then we move disk number 64, right? Now, if you just think about 63 disks that are all on needle 2, to move disk number 63 from needle 2 to needle 3, we first need to move the top 62 disks from needle 2 to needle 1. If you notice as I'm talking, we are basically redoing the same thing for case of 62, and then we're going to do it for the case of 61 and case of 60 and so on, so forth, okay? So if you look at it like this, then for a positive n, we just need to move the top n minus 1 disks from one needle to the other one, and then move the next n minus 2 disks, okay? Let's go to the code and see how this recursive algorithm could be depicted in the code. So our recursive algorithm translates to this function moveDisk that we have over here. Let's go through it together. So the moveDisk function receives an integer count, which is the number of disks, an integer needle 1, needle 2, and needle 3, which are the 3 needles. So what we check is, we check if count is greater than 0, which means we have a disk, because if you don't have a disk, then there is no algorithm needed, right? So if we have a disk, we call the moveDisk, which is the same function, over count minus 1. Remember how recursivity works? Now it's working over count minus 1, passing the same 3 needles as our needles. And then a message that says, cout, moveDisk, and it tells us disk number what, disk number 2, 3, or whatever, from number of needle 1, needle 2, needle 3, whatever number or identifier we have over there, which in this case could be just 1, to needle 3, right? And this basically is the first part, okay? So for the second part, the only thing that we need to do is we need to call the moveDisk, okay, over count minus 1. And of course, needle 1, needle 2, and needle 3. So needle 1 is going to be here, needle 2 is going to be here, and needle 3 is going to go over there, and of course terminating the line, and that actually completes the algorithm that we wanted to do. The fun fact here is if you suppose the Prist can move one disk per second and not rest at all, the time required to move all 64 disks from needle 1 to needle 3 can be calculated to roughly 5 times 10 to the power of 11 years. That is 5 with 11 zeros in front of it. It is estimated that our universe is about 15 billion years old, which is like 1.5 times 10 to the 10. And this calculation shows that our universe would last about 33 times as long as it already has if the Tower of Hanoi is actually true, which is not. But anyway, as you can see, it's an amazing and very effective way of keeping people busy while knowing they will never reach to the result. Anyway, let's for before we finish this video, let's talk about the decision making over recursion or iteration. You see, there are usually two ways to solve a particular problem: iteration and recursion. The obvious question is which method is better, iteration or recursion? Honestly, there is no simple answer. In addition to the nature of the problem, the other key factor determining the best solution is basically efficiency. Okay? While tracing the execution of different recursive functions, you can show that every recursive call has its own set of parameters and automatic local variables, right? That is, every recursive call requires the system to allocate memory space for its formal parameters and automatic local variables, and then deallocate the memory space when the function exits. Thus, there is overhead associated with executing a recursive function, both in terms of memory space and computer time. Therefore, a recursive function executes more slowly than its iterative counterpart. On slower computers, especially those with limited memory space, the slow execution of recursive function would be very visible. Today's computers, however, are fast and have inexpensive memory. Therefore, the execution of recursion function is not that noticeable. Keeping the power of today's computers in mind, the choice between the two alternatives of iteration or recursion depends on the nature of the problem. Of course, for problems such as mission control systems, efficiency is absolutely critical, and therefore the efficiency factor would dictate solution method. As a general rule, if you think that an iterative solution is more obvious and easier to understand than a recursive solution, use the iterative solution, hands down, which would be more efficient. On the other hand, problems exist for which the recursive solution is more obvious or easier to construct, such as the Tower of Hanoi problem that I just went through. In fact, it turns out that it's difficult to construct an iterative solution for the Tower of Hanoi problem. I'm challenging you try to solve this problem through iteration, not recursivity. As you notice, we only here have line 6 to line 12 as solution to this, which really is nothing but 4 or 5 lines. Try to do this in an iterative way, and you can see that is really complicated. Keeping the power of recursion in mind, if the definition of a problem is inherently recursive, then you should consider a recursive solution. And here I'm concluding this video. Thank you for watching, and see you in next video.